Hello, everyone, and welcome back. I would like to bring you all to what will probably be the last video on Chapter 1 in the textbook, which is on the subject of continuity. This is it seems a little bit different than limits, but it is a concept that's about limits, so it does fit in with the rest of the section, but there are some other ways to talk about it other than just in terms of limits, and we'll talk about both of those ways to look at it as we go on. And then I'll have you look at some examples, and we'll do a couple of problems based on that. Okay, so first of all, we have a couple of different ways to describe continuity, and usually the common way when you're introducing first-year calculus students to this idea is the following statement. And here, let me zoom in, but not too much. All right. So, if you can draw the graph of the function, any place you have to pick up your pencil is a place where the function isn't continuous. So, let me underline this here. So, anytime you pick up your pencil when you're drawing the graph of the function, that's a discontinuity. So when we say the function isn't continuous, that's the same as saying a discontinuity. Sorry about that. That's a little bit sloppy, but it should do. So some functions you'll see are continuous everywhere. And by that I mean if you drew the whole graph of the function, you'd never have to pick up your pencil. So why don't you pause the video and think about some graphs that we've seen so far that you might expect to be discontinuous, and maybe what points you would see those be discontinuous at. And this can either be from the videos or the book, whatever makes it easier for you. Okay, so if we're back, here are some ideas about what makes a function not continuous. Hang on, let me zoom in a little bit so I can write a little bit clearer. So, what makes a function not continuous? And remember, one way of thinking about this is if you have to pick up your pencil. So the places you would have to pick up your pencil are the following. So anytime we see one of the following things: a gap or a jump, and I'll draw a little sketch of that here in a second, or what we'd call a hole in the graph. And we've seen examples of both of these either in the videos or in the book so far. So let me draw some quick sketches of what those might look like. Okay, so first of all, let's talk about this first one, a jump. Let me put this in blue. So if we have a jump, it would look something like this. And this will be a little bit of a small sketch here, but it should give you the idea. So if we have a function that does something like this, and then it jumps up here and does something different, we've seen graphs like this in the book. That is an example of a jump. And an example of a hole in the graph would be something like this, and we saw this in our first video. It doesn't matter what the function starts out as, but something like this. and then there's this place where the function is undefined. I think I kind of didn't sketch that out the way I wanted to. Let's see. It doesn't matter. Doesn't have to be perfect here, but let's go ahead and try and make this roughly what I want here. So let's say we've got something that looks more or less like a parabola here. And so it's just like a parabola at every point except this one right here, and that is where it's discontinuous. Just like up here, that point right there is where it's discontinuous. So those x values are what we're talking about here. So this x value right here, oops, I think I gotta zoom in a little bit. There we go. This x value is your discontinuity. And we're gonna have another one down here at this point. Obviously, that's the x value. The dotted line doesn't mean it's an asymptote or anything. It just means that's the x value where we have a discontinuity. So that's the way to tell about where a function might not be continuous about a graph. A second way to talk about continuity that I think is maybe a little bit more useful even in doing what we're doing is this. Any place where you can find the limit by simply plugging in is a place where the function is continuous. So in other words, all the nice examples that we saw so far, all our nice examples, so like for instance, if I gave you the limit as x goes to 4 of x squared minus 2x plus 3, that's an example of a function that's continuous, and it's continuous at 4 here, but it also happens to be continuous everywhere, because in order to find that limit, all we've got to do is plug in 4 squared minus 2 times 4 plus 3. So whatever that winds up being, 8 plus 3 is 11. All right, so that's an example of where the function is continuous. So for a function like this, a polynomial like this is going to be continuous everywhere. So that is continuous everywhere. That's not true of all functions, even some where we have places where they are continuous. Sometimes they're continuous most places, but not every place. As you can see on these two graphs that we saw here, even these functions are continuous most places, right? They're continuous except at these 2 points that we've drawn here, where there's the jump or the hole in the graph. Okay. So let's talk about examples of continuous functions. And we already mentioned one, which is polynomials. And this basically means all polynomials. So any example like y equals x plus 1 is a polynomial. Y equals 3x cubed minus x squared plus 2. These are all examples of polynomials. Let's do another one here. Y equals x squared, or even y just equals a constant. That technically counts as a polynomial as well. So something like y equals 6. anything where you have your function is written as sums of powers of x, maybe times a constant in front. So like for instance this first one, x plus 1, that's x to the first plus a constant, that's a polynomial. This one here, x cubed, that's x to a power, x squared, that's x to a power 2, that's a constant, and these are all added together and maybe multiplied by constants. That's all you have to do to have a polynomial. So that's one example of a continuous function. Two others that are fairly common, and there are more than this, but these are pretty much what we've got to work with so far. Some of the other ones that you'll hear about are exponentials, but we don't get into that at this point in Calc 1. So I'm not going to go into that in too much detail. But so y equals sine x is also continuous, and not just continuous, but continuous everywhere. And so is y equals cosine x. So sine x, cosine x, those are also both continuous everywhere. So these aren't just continuous functions, these are continuous functions that are continuous everywhere. In other words, every single x value. If you ever want to find a limit of one of those, all you've got to do is plug in the value that you've got, and that is all you need to worry about. Now, you'll notice I also have a slightly more complicated version here that says most functions made from these types. So, in other words, what I mean by this, and this is a little bit trickier, but let me explain here. What I mean by this is any sum, so adding them, difference, so that means subtracting them, or product. Let me zoom in just a little bit more. It's going to make it a little bit more readable for you later. Of these types of functions. And again, sorry about this. If there was a better way to do this, I suppose I could type, but you know. Well, I said, but you know, but who knows why somebody does more work when they could do less. Okay. Oops. Let's see. So, any sum, difference, or product of these types of functions are automatically continuous everywhere as well. So, like if I have f of x equals 3 sine x plus x squared minus 1, that's continuous. This one is continuous everywhere. That is continuous everywhere because it's a sum of products that are already of those types. But you can get more complicated and it still works. So f of x equals x squared times cosine x. That also is continuous everywhere. Or even sine x times cosine x. Even sine x times cosine x. That is also continuous everywhere. And not only sums, differences, and products, also what we call function compositions. And what that means is when we plug one function into another. So let me write that here. So I know I just said it, but it'll be better because you'll have it written out on the PDF. So when we plug one function, I'm abbreviating function here, into another. So let me do an example or two of that sort here. So for instance, an example might be f of x equals cosine of 3x cubed minus 4. So here we have 3x cubed minus 4 plugged into cosine. That is still continuous. Also, we can plug it in the opposite way. We can have sine x squared. So here sine x is plugged into the function which would be something squared, in other words, x squared. So here these are all continuous everywhere, every single one of these. I only wrote the line here, but this one, hang on, this one, this one, this one, this one, and that one are all continuous everywhere. Okay, so hopefully that makes sense. Now, you will notice probably that I mentioned a lot of different operations. I'll use green. And a lot of different operations that we could do to combine functions. I mentioned sum, which is adding, difference, which is subtracting, product, which is multiplying, and even function composition, which is plugging one into another. But if you will think about this and think about different operations you can even do to numbers, there's going to be one that maybe is obvious that is missing. So you might want to pause this video if you haven't figured it out to try and think what else might be missing here. But I will answer that now. And this is also an example of functions that are continuous. So also, well, we added, subtracted, and multiplied, so obviously the next one is divide. So we would say quotients of continuous functions. But there is an exception here. That's why I didn't put it with the first one. And you can probably even guess what that exception might be, because what is it that gives us trouble when we divide? What are we not allowed to do when dividing? Well, as long as the denominator isn't 0. There we go. So, also quotients of functions, as long as the denominator isn't 0. So let me do an example or two here. Hang on. Let's do the first one as a polynomial, and easy enough. Hang on, I need f of x, or I don't need it, but I should put it there. Don't absolutely have to have it, but x squared minus 1 over x plus 2. So this is an example of a quotient of functions. So this is also continuous, and it's continuous almost everywhere. So this, we would say, is continuous everywhere except... Oh, I did that in red, didn't I? Let's do it in red again. Continuous everywhere except where we saw what we said was the denominator equals 0. Well, if we look back at our denominator, it's x plus 2. So we don't want x plus 2 equal to 0. In other words, where x is equal to negative 2. This is where the function is discontinuous. So it's discontinuous only at x equals 2. Everywhere else it's continuous. So everywhere except where x is negative 2. That's the only place that it's discontinuous. So that's one example. We can get into some that are more complicated. Let me do one more example of that type. So here, this one might not be obvious how it's a quotient, but let's talk about it. Tangent of x. So you'll notice up here we did say two of our trig functions, sine and cosine, are continuous, but we didn't talk about tangent. And now I'm talking about quotients, and I'm saying that that tangent is not continuous everywhere. So what I seem to be saying here is tangent is somehow a quotient of two functions. And you may not remember this, but if you do, this is, what is it? Sine x over what? Cosine x. And if you want to remember that, let me draw the little thing up here. The right triangle. Try and make it look good. So we would have, this is our angle. We have our hypotenuse. We have our adjacent side. We have our opposite side. And if you remember, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. This is all review, but it's worth reviewing. And tangent is opposite over adjacent. Now you can actually divide sine by cosine and the hypotenuses cancel out, and you wind up with tangent equal to sine over cosine. So sine over cosine is the same thing as tangent. Now this one then is continuous. This one's a little bit more complicated. This is continuous everywhere except where cosine equals 0. Now, that's true, and it's, something that does explain it, but you do have to remember where cosine is equal to 0, and if you recall that, hang on. this is cosine equals 0 at, well, you have to remember your unit circle here. So if you don't have that, you might want to look it up. Maybe I'll put it on here later, but we'll see about that. It might take a little bit more time than I'd want. But cosine is, remember, sine is 0 at an angle of 0 and an angle of 180. Cosine is 0 at 90 degrees. In other words, in terms of radians, pi over 2. 270 degrees, which is 3 pi over 2, and so on. And when I say and so on, what that means is anytime we go fully around the circle, we wind up at the same place again. So the way to actually write this out would be pi over 2 plus any multiple of pi. Because if we go around the circle once from pi over 2, we're at 3 pi over 2. If we go around twice, we're back around at pi over 2. So we get pi over 2 plus k pi, and here for any integer k. And we say an integer here because it could be a positive number, then you're going around the circle counterclockwise. But if it's a negative number, you're going around the circle clockwise, and either way you wind up where you started. So k is any integer. So this is an example of where that one would be. This first one was just discontinuous at x equals -2. The second one is discontinuous at pi over 2, 3 pi over 2. Then we add pi again, we get 5 pi over 2, 7 pi over 2, 9 pi over 2, and so on. And we also get the negatives of all those. So minus pi over 2, minus 3 pi over 2, and so on. That's just an example of where the denominator being 0 makes the function not continuous. Okay. Let me highlight these things the same really quick so everybody can see what's going on. All right, so hopefully that makes sense to everyone. That's most of what we want to do with continuity. But there is another thing that we want to talk about, which is the difference between what we call a removable discontinuity and a non-removable discontinuity. And fortunately for us, right there, let's go down here. Fortunately for us, we've already talked about this, just not in this language. So if we have what we call a removable discontinuity, all this really means is the same thing we talked about before as a hole in the graph. So where the graph, you can draw it with a pencil, except you have to pick up your pencil at just one spot where the function's not defined. So this is one place where the function is undefined. Okay, so actually let me move that down a little bit. There we go. Move this one down with it. There we go. So this is an example of, actually, let me actually line this up because it will do that for me, so that's worth doing. There we go. Okay, so it's just a single place where the function is undefined. In other words, we're drawing the function and then we have this gap. Now, sometimes this isn't just where the function is undefined. Sometimes they will actually put another value. Let me show you what I mean here. They would actually put another value where the function is defined. So you're going along fine, like that, and then you get to this point where the function has a hole in the graph, And they might say, well, we'll define the function as being this value up above, even though it's not where we would expect the point to be. So that is still sort of technically a jump, but we would still call that removable discontinuity, and we'd still call it a hole in the graph, because other than that one spot, the function is heading along the same route. So that's an example of what we call a removable discontinuity. However, we also have another type, and you can probably, at this point, even guess what it might be called, because we're not that clever. It's called a non-removable discontinuity. I'll capitalize it, why not? It'll make it feel better about itself. There we go. All right. So this is what we call a non-removable discontinuity. And there are a couple of examples here. Again, one of which we've already seen. Let me put that one here. And that one is a jump in the graph. Or, and I'm going to put another example here, but it's a pretty rare one. There's an example of it in your book, and we'll talk about it here. A place where the function oscillates really fast at a single x value. And we'll talk about that example in a second. But the most common case here of a non-removable discontinuity is what we saw up here as a jump. Oops, what happened there? I don't know about that. Okay, so we might be doing what we were doing with the hole, walking along the graph, and then we have to jump all the way across this chasm here to go down the other side, right? We have to jump across that chasm because, the bridge is out. And we're on our way to find the treasure. All right, so that's the idea of what we mean by a jump. Now, on oscillation, there are functions that oscillate, and that doesn't necessarily mean that they're discontinuous. But let me show you an example of a function that oscillates and is discontinuous. Sine of 1 over x. And this was an example in, I believe, the first section of your book. So here, we might have our function here. If we have sine, I haven't gone over what it looks like, but let's do it real quick here. If I have y equals sine x, this one is continuous, and the graph of it looks roughly, I don't want to get too deep into where the points are here, but the graph looks, I think I've got a little, nope, don't have much more room. I can't do this though. And let's see here. Yeah, right about there. So sine of x starts off at 0. It winds up going up to 1, then bounces back down to 0, then goes down to -1, and it repeats when it goes in the backwards direction. Hang on. Let me not mess that up too bad. Any worse than I have to, anyway. So sine looks like this. It's sort of this wave function. If you've heard of sine waves in electronics and stuff, that's essentially what you're talking about. But that's the shape of the sine of x. Sine of 1 over x does something similar to some extent, but the fact that what you're plugging in has a problem at 0 causes some really weird things to happen. And essentially, I don't want to worry about what happens when you go further out from 0. But think about this when you're going close towards 0. That value, that 1 over x there, that thing is getting, not when you're going close to 0, when you're plugging in bigger and bigger x's here, right? So when you're Oh no, sorry. Let me rephrase this again. Yeah, when you're plugging in values that are really close to 0 here. So right, let's do this here. If we do x close to 0, if you do x close to 0, what you're going to see here is this function is going to keep getting bigger and bigger. But when you plug that into sine, it bounces back and forth, right, between 1 and -1. So what happens as you go in towards 0 here, I guess I'll actually show it in red here, and don't worry about where all these points are. What happens is it bounces up and down between -1 and 1, like that. So, you know, looks awful, right? You know, somebody just painted blood down the walls there, right? So it bounces up and down, and you can figure out what it is at any point away from 0. You can figure out the exact value. But once it gets to 0, it's undefined, and we don't have any way of figuring out what value it is between 1 and -1. So this is an example of an oscillating graph right there. This is pretty much the only example that you're going to see in Calc 1, but it's relatively easy to make these kind of graphs out of different trig functions. Okay, so hopefully that makes sense. Now, we are almost done, but I do want to talk about why do we call removable discontinuities removable. So why are removable discontinuities removable? Okay. There. Okay. So why are they removable? Well, the answer to that is pretty straightforward, actually, if we look at the picture up here. Remember, a removable discontinuity was like this hole in the graph, right? Well, that likes to jump around. It's like this hole in the graph. So why that's removable? All we would have to do is change what the value of the function is at that point, and it would become continuous. In other words, the limit for that function is the same on both sides. So here, that's what we want to say here. If we just change the function's value at a single point, it would become continuous. But in other words, hang on, I wanted to hit enter there. In other words, it has the same limit from both sides. So that's what we mean by a removable discontinuity. Something like that. Okay, so let's actually take a quick look at an example. And what's useful for this kind of example is what we call a piecewise defined function. This is something you probably saw in a pre-calculus class, but it may have only been briefly mentioned. So let's talk about what we mean by a piecewise function. this is what we would have essentially, and some of you may have already seen this in the homework, a function that has different functions here for different intervals. Oops. Okay, so let's take a look at what we mean, an example that we could have for that. Oh, that is not what I wanted. Okay, hang on. So, example, let's say we have f of x equals, when we have a piecewise function, we're going to have at least two pieces. You can have more, but I'm only going to stick with two here just so it's something we can handle. So let's say this one is x plus 1 for certain values of x, and then it is 2x at other values of x. So let's say it's x plus 1 for all x less than 1, and it's 2x for all x greater than or equal to 1. It could be greater than or equal, or it could be greater than, and just the function would be undefined at x equals 1, but usually it's defined everywhere if you're going to make it piecewise. Okay, so this is an example of a piecewise function. Now, how this ties into a removable discontinuity, essentially, there are two things you could do here. You can graph both pieces of this. So you would graph this first one. On all x values, you just use that function up until you got to the point x equals 1. So you'd make out a chart for x equals -3, -2, -1, 0, and then some partial values in there until you get up to x equals 1, and then you stop using that function because then the piecewise function switches to this second one. And then you have the function equals 2x for x equals 1, 2, 3, 4, and so on. So, actually, let me draw this out here. It'll be pretty easy. Relatively easy. This line's going to be a little crooked, but it will look better when I zoom out, so I haven't figured out how to make this thing draw straight lines for me, so, what are you going to do? And I don't have to have all the values here. So what I might do is I might plot values. So let's actually think about what that would mean here. If I plugged in, that first part's going to get a little bit big because we have that x squared. But if I plugged x equals -2 into that, well, -2, I actually do need to make this a little bit bigger, at least to get that part. If I plug -2 in there, -2 squared is 4, plus 1 is 5, so -2, I should have -2, 1, 2, 3, 4, 5, so I should have that point at -2. At -1, I should have -1 squared is 1, plus 1 is 2, so I should have this point right here. And let's get rid of these. I'll have to refill in the blue in a second, but that's blue. Let's do that. Okay, and that one, that'll do. Okay, one more. Okay, so that's what I get if I plug in -2. Then I would plug in 0. If I plug in 0, I get x squared is 0 squared plus 1. So 0 plus 1 gives me 1 right there. And that's the last whole number I can use there because I'm looking at only x going up to 1 but not including 1. I could still get some more values, and what I would see if I got some more values, so if I plug in a half squared is a fourth plus 1 is 1 1/4, so we would get something like this. We would have the same thing on the other side. If we plug in 3/4, we get even closer. Essentially what we would be seeing here is we get a function that goes up to that point, up to where we get to this point right here, this point 1, 2, but it doesn't quite reach it. Okay, so that's what we would see there. Now, on the other side, if I start at x equals 1, and I plug that in, I get 2 times 1, which happens, in this case, to fit right at that exact point that we were heading toward on the other side. So, but then at that point, I still use y equals 2x from then on. I don't get this y equals x squared anymore, or x squared plus 1 anymore. I use y equals 2x now. And so when I plug in 2, I get 2 times 2, which is 4, and so on. We don't really have much to do after that point. But what we get there is, so this direction, hang on, this direction we have a parabola. This direction we have a straight line. So the function is made up of 2 pieces. But you'll notice they come together right here. So they have the same limit. From both sides. And that, well, in this case, means that the function isn't discontinuous at all. But even if I had this function with a different value here, no matter what that value was, let's say I had a hole in the graph there as well, and I made the value up here, all I would have to do is change this to that value, and it would show me that this is this function would have only a removable discontinuity. So, same limit from both sides. So in this case, even if the function isn't defined, at that point at the hole, the discontinuity would be removable. And the way to tell that is just to take the limit from both sides. In other words, you would have to check. Let me change that to blue. The limit as x goes to 1 from the left of f of x, and the limit as x goes to 1 from the right of f of x. And both of these were defined differently, so we would actually use those functions. X goes to 1 from the left. This first one was x squared minus 1, or sorry, x squared plus 1. The second one was 2x. You'd have to check these, and these would need to be the same. And that's for the function either to be continuous, or if the function's even not defined at that point, for the discontinuity to be removable. And hopefully that makes sense. I think that's it for today, but I will be posting this. But by the time you hear this, it will already be posted, because, again, if I haven't said that before, that is the way time works. All right, so I will talk to you all later, and if you have any questions, please let me know, and hope everybody is doing okay. Thank you.